Our next speaker is Curtis Lee, who is going to first of all, switch out computers, and we'll talk about his physics project. Curtis is a dual major, physics and math, so tomorrow he's going to give his math presentation. The committee awarded him for the physics presentation. Curtis is going to start at Duke next year as in a PhD program in physics. He's going to, his talk tonight kind of gives you a preview, I guess, of some of the things he plans on studying. And he's gotten several awards from Duke and from other agencies, and so he's going to be quite well funded at his next position. So welcome, Curtis Lee.
Thank you, Dr. Jonas. Before I explain the meaning of my presentation, let me give a little bit of background. I spent last summer at Duke University studying in the engineering department and trying to implement some new methods for modeling the behavior of ocean waves with computer simulations. The interaction between ocean waves as well as floating solid body objects. Of particular interest is not only the two phases, both the fluid phase and the air phase, but also the boundary between water and air, the surface of the water, which is known in the computational fluid dynamics community as a free surface. And so this presentation will focus primarily on the gradient augmented level set method, which is kind of a new method developed just this past year for modeling the boundary between water and air. So why are we interested in modeling ocean waves and their interaction with solid bodies? Our motivation comes primarily from the development of energy harvesting buoys that actually float out in the ocean, can collect kinetic energy of ocean waves, convert it into stored energy, electricity, and be used to power things. There are two real categories behind this. One is a standalone kind of isolated buoy that floats in the ocean and is used to power things like weather buoys like you see here, as well as, if you've been following the developments in Japan, buoys that can detect drastic changes in ocean level in worn coastal areas before tsunamis strike. But in addition to powering these isolated buoys, we also have a vision, if you will, of fleets of these devices, buoys that can convert kinetic energy into electrical energy, a fleet of them tied together that can produce enough energy to power cities, things that can be relieve our dependence on fossil fuels, on coal, on natural gas. So here we have a two-dimensional representation of what we'll be working with, and this is all in 2 dimensions. We'll be seeing some videos later on. We have, of course, the water phase, the air phase, and what's known as the free surface, the boundary between water and air. Here's our first demonstration. This is what a typical simulation looks like for us. We have a water phase at the bottom, an air phase at the top. You'll see we have a wedge on the left side that's driving the motion of the water. We have this nice free surface illustrated here between the water and the air phase and our buoy object that's floating in the center on what's now a standing wave. And most of this presentation will focus on how we're able to produce these objects, how we're able to represent them computationally, and how we're able to show the fluid advectum. What we can do is add internal dynamics to our buoy. That's how we go about actually collecting energy, is we have a spring mass damper system, in this case a rotational one, that is able to damp the motion, the internal motion of that buoy, convert that energy into stored energy, much like they have watches now that are charged by the motion of your arm. It's the same concept. You can use things like solenoids as well to store that energy. This next simulation, there are a lot of blue arrows in the background. Those represent the velocity at a particular point in the computational domain. So where you see more blue, things are going more quickly. Let me start that one. This is an example of an instability. Anytime you work with computational physics or engineering, you always risk instabilities that arise from either typos or methods that don't quite align correctly. This, we suspect, is a result of the level set method here. That's not natural at all. You see, those are the things we try to avoid typically when we're developing these simulations. So that's as a result of using the classical level set method. We're in the process right now of moving to a gradient augmented level set method to represent that boundary between the water and air phase, and that's what we'll talk about here today. But first of all, the classical level set method is used to represent two-dimensional bodies. Like you saw in the previous simulation, we had buoys, we had the boundary between the water and the air, and we had that wedge driving the motion. Those are two-dimensional bodies, but we can't just, it's not very easy to model those things in these computer simulations. So what we do is develop a three-dimensional, it's called a level set function that exists on the entire domain, is actually advected by the velocity field in the background on the entire domain, and all we're interested in is a tiny slice of that 3D function. So here, this slice gives us that, this slice gives us that surface, and this slice gives us that surface. And that's how we generate the boundary between water and air and the buoys and the wedge that you saw in the previous simulation. Here's a look at the computational domain. It's split up into rectangular grid cells with nodes at each corner. Information about the level set function itself is actually stored on those gray nodes. And actually go about implementing the level set method. We have the level set equation, which acts kind of like a conservation equation. It basically tells us that the fluid velocity, and only the fluid velocity in the background, drives that 3D level set function and drives the motion of our 2D bodies. For the purposes of the classical level set method, it's good to maintain this function as a sign distance function. That requires a few more steps, a reinitialization equation, as you see equation 5 here. This is what we think is responsible for the instability that arose in the previous simulation. And this is something we're moving away towards by implementing the gradient augmented level set method. It has several advantages. Instead of just storing and advecting the level set function itself on the entire domain, what we're actually doing now is storing gradient information about that function and advecting it with the fluid flow right along with the level set function itself. This allows us for much higher accuracy because now that we have gradient information, we can go ahead and interpolate cubically over the domain, whereas the standard level set method only allows a linear interpolation. So this allows for better volume preservation. It permits subgrid resolution because we can see between those nodes that you saw in a few slides back. It's also designed to be optimally local, which means that all of your calculations can be done on just one of those little grid cells, whereas with the previous method, you have very large finite difference stencils that require much greater patch to do similar calculations. In addition, derivative quantities like curvature and normal vectors and things like that are very easy to derive using a gradient augmented level set method because we already know the derivatives at every point on the domain. So here's the gradient augmented level set method. We have the same equation that we had before, but now we take the derivative of that equation and we have an expression for the gradient. Here where psi represents the gradient, phi previously represented the level set equation. And cross derivatives are calculated on the fly with the standard central difference method. Here's the equations for the Hermite cubic interpolation I mentioned previously. So now we want to go about solving these two equations. These are our two representative equations. That's not an easy task as they're presented at the top of the slide, but if you observe, these actually represent the material derivative of their level set function and the gradient, respectively, along that velocity field. So if we can calculate at each node the distance curve from a previous time step, if we can move along the displacement curve, this simplifies these equations drastically. It removes the velocity from the left side of the equation. So now we break it up into two steps. We must calculate this distance, and we have to calculate these equations, which are much simplified than before. And that's all accomplished with the super consistent Shu-Osher third order Runge-Kutta method. I won't go into much detail with that. So once we've implemented all these things, we have an example. These are the equations for the next example we'll see. And these are the author's results for this particular example. What's going on here is, if you will imagine a coffee cup with a drop of creamer added just at the top. And we're going to pretend that it doesn't sink, it doesn't dissipate, it just sits there while the velocity in the background is still. What we're going to do is go ahead and spin that cup. We're going to create a vortex in the middle of it, and you'll see this twisting motion. That's our drop of creamer twisted after 4 seconds. But our velocity field is so chosen that after 4 seconds, it will reverse direction. And the idea is that analytically, we'll get back to where we started. So this gray area represents where we started and where we'd like to get back to. So looking at the gradient augmented level set method, it's represented by this blue outline here. it does a pretty decent job. It achieves about 80% volume preservation. The red outline is the older, the classical level set method that we used in those previous simulations, and it does a much poorer job compared to the gradient augmented level set method. So I was able to reproduce these results that the authors gave. Here's how that actual simulation looks. The green circle represents where we started. It's not physical, it's just for reference. The whole goal here is to get back to where we started, get back to that green circle. If this were purely analytical, if we had the exact solutions to this, we would get back to that circle. But of course, since this is all approximation, this is all computational engineering, there's guesswork at every step. So the closer we get back to that green circle, the better. Back to our initial condition. And this does a pretty good job. These are the same results that the authors achieved. But if you recall, a few slides back, when I first mentioned the level set method, we're not actually moving around just that two-dimensional body. We're actually generating this three-dimensional level set function, and we're pushing it along at every point in the domain. So what does that actual three-dimensional level set function look like? What does the big picture look like? And it looks like this. This is the same simulation. The white outline is the same outline that you saw on the previous slide. Again, like I said before, we're just slicing that level set function. And you can see it twist and create that same curl. And then change direction. But it shows you the amount of work that goes into generating just that sliver that you saw on the previous slide. We have to advect this entire function on the entire computational domain. And so the goal is to get back where we started, and this does a really nice job of preserving where we started. The challenge, one of the challenges with the gradient augmented level set method is far superior to the classical method. One of the issues we face is that it demands that the velocity field be known at every point on our computational domain. That's not typically the case for most fluid solvers, for most actual applications. Typically, it's more typical that you only know the velocity at certain discrete points in time and certain discrete areas in space, because your velocity field is actually generated at the same time that your level set function is generated. So trying to move towards a more discrete version of the gradient augmented level set method, I took a step back and said, okay, well, let's say we don't know the velocity field at every location. We just know it at these nodes. How can we bridge the gap? And I took it a step further and used bivariate Lagrange interpolation on the entire domain. Knowing only the velocity field at the nodes, we now can extrapolate that, or interpolate it, excuse me, everywhere else in the domain. And the top portion represents the x direction velocity, and the bottom portion here represents the derivatives of that. For the y direction, the equations are similar. This actually produced very nice results. The results of this were actually indistinguishable from the results from the actual gradient augmented level set method as it's presented by its authors. So I was very pleased to see that. I wanted to see where a difference would occur, though, where you'd begin to see a difference between this interpolated method and the gradient augmented level set method. So I began to use a coarser and coarser mesh, fewer and fewer cells, watch the quality of the simulation degrade until I began to see a difference between the two methods. And finally, using 32 by 32 cells, there's a small difference. The red represents the gradient augmented level set method as it's presented by the authors. The gray represents my interpolated method. And you begin to see a little bit of a difference. But fortunately, it's still surprisingly accurate. You get near the same, almost more volume preservation with the interpolated method than you do with the gradient augmented level set method. So this is really promising because this shows that we can actually incorporate this into the buoy simulations that you saw in the first few slides. This can be used to prevent instabilities like you saw and provide a little more volume preservation, a little more accuracy in our simulations. So in the future, I'd like to add that to our buoy code. I'd also like to work on some experimental verification in Duke University's wave tank. More complex internal dynamics are the next step. The whole idea behind this project is to see how we can optimize these energy harvesting buoys to get the most efficient structure that we can. And the whole idea behind computational science is to do this in a cost-effective manner, do this on a computer. That way, when you're ready to actually design a product, design something that can be used in industry, you have a really good idea of what you're doing. You're able to optimize it well beforehand. An extension to 3 dimensions is in the works. That'll require some parallel computing and its own set of challenges, but that's hopefully a couple years down the road. I'd like to thank my advisors and friends at Duke University, as well as Dr. Davis for helping me as I worked on the gradient augmented level set method for my senior seminar this semester. And here are my references.